Welcome to the first colloquium, computer science colloquium for 2014. We're very pleased to have Shai giving the colloquium today. Shai did his undergrad, I think, and graduate school at Hebrew University in Israel. He was then a postdoc at the University of Toronto, first of all in the mathematics department, and then in the computer science department, where I first met him in the mid-'80s, when I was a very young master's student. Shai then went to Technion for quite a number of years. He was a professor there. He was a visiting professor at Cornell, I think Australia in the middle of that, and came to the University of Waterloo in 2004. And we're very pleased to have him here since then. And it looks like we have a very interesting talk for today, understanding machine learning from a theory perspective.
Thank you.
Thank you, Shai.
Yeah, thank you. Okay, thank you. Yeah, so I'll try to give an outline of the way I see machine learning, which is a theoretical theory view. And I like to start those talks usually by this citation from Herbert Simon. Herbert Simon was one of the pioneers of AI and got Nobel Prize in economy and Turing Award. And he said that the purpose of science is to find meaningful simplicity in the midst of disorderly complexity. And I view this as a good definition of what is the purpose of machine learning. We have very complex data, very huge amounts of it. For humans, perception, it's completely doesn't make any sense. We're trying to apply machine learning to find some meaningful simplicities in this complex data. Okay, so this is what statistical machine learning is about. It's concerned with algorithms that find meaningful regularities in large complex data. We focus on kind of patterns which are too complex for human to perceive. And we consider finding such regularities from random samples. So we look at a task where you've got a random sample of your big data, and you're trying to draw conclusions about the whole data set just from these random samples. And what kind of task do we want to handle? Some tasks are too difficult to write program for. And what we wish to do is write a program that will learn how to write a program to carry out the task. So we cannot directly instruct the computer how to do things. So we want the computer to learn how to write the program that will do the job. And such tasks are, for example, speech recognition. If you hear voice and you want to decrypt what is being said, we cannot fully understand how we do it. We cannot write a program to do it. But we can write a program that will eventually learn to do it and develop itself. Similarly, for driving a car, you know that now we have more and more autonomous drivers. And again, the task is too difficult to program explicitly. Instead, we have the automatic driver that sits there, and whenever he runs over someone, he gets a punch. Whenever he drives nicely, he gets a carrot, and eventually he learns how to do the job. And spam detection is another such task, and categorizing documents, lots of tasks which are too difficult to program directly. We want just to have a program that will learn how to do it. Okay, so the typical setting, just to give you a concrete setting of what we're talking about. So assume you want the computer to write a spam detector. So first of all, you have to extract some relevant features. So say features like the return address, keywords, spelling, etc. You extract those features, and then you get a sample of emails which are labeled whether they're spam or not, and you want to give this as a training input to your algorithm. So the training sample can look like this. Each row is an email, and for each row, we just mark yes or no, whether it talks about sales or talks about sex, or have the word Mr., and so on. And at the end, we label it whether it's spam or not. And we give this as a training input to the program, and you want the program to come up with a rule that will distinguish spam emails from non-spam emails. So such rules could be, say, based on the table that we just saw, such rules could be, say, predict spam if unknown sender and it has sex or sales. Or predict spam if the sum of sex plus sales minus known is greater than 0. It cannot come up with some such rules, and we want the computer to find such a rule automatically, just based on a training data. So these are called classification prediction. We are trying to predict the classification of the email, whether it's spam or not spam. And it's a subset of machine learning. And there are many tasks that fall into this category of classification prediction. Say medical diagnosis, we want to predict whether a patient is in high risk or low risk. We want to do a sequence-based classification of proteins, or to detect whether some transaction on your credit card was fraudulent or not. All of those are tasks which are classification prediction. We want to predict whether the class is yes or no, 0 or 1. OK, so let me start with discussing how animals do it. And this should have been a rat. Someone told me that maybe it's not a rat. But rats are known for being very smart at learning when you try to poison them. So it's called the bait shyness phenomena in rats. And the bait shyness is that when rats encounter poisonous food, if they see food that they haven't seen before, they take only a very small taste. And if within a few hours later they feel sick, they attribute the sickness to this tasting of the new food, and they will never touch it again. And this makes it very difficult to poison rats. And today's modern poison for rats, they have delays. So the rat tastes this food, waits a few hours, feel happy, everything is good. So it goes back to this food, eats more, and a week later, boom, it all comes out. So from our point of view, the question is not how to poison rats, but how come the rats managed to learn which tasting was to blame for feeling sick from just one experiment? I mean, the rat cannot afford to have tens of experiments. Sometimes it will fail to detect poison, sometimes it will not. It cannot afford it. So how come the rat can do it so nicely? And we want to use it as some of guidance to direct us of how to write program that will learn to detect patterns. So there was an interesting follow-up. This was a known phenomenon. There was an interesting experiment carried out in 1989 by Garcia, that he found that when the stimulus that precedes the sickness is sound rather than taste or smell. So now we do the experiment differently. We give the poison in food that looks and smells exactly like the food that the rat gets every day. But when the rat gets the poisonous food, there is some special sound. A bell rings. Now the question is, will the rat, when it gets sick 5 hours later, associate the sickness with the ringing of the bell, and the next time if it given food and ring a bell, it will not touch the food? What do you think? Well, it turns out that it's not. The rats fail to detect the association and do not refrain from eating when the same warning sound occurs again. So somehow the rat was sensitive to clues that had to do with the shape and the smell of the food, but is completely ignorant of the sound that occurred during the feeding. So why is it good? I mean, maybe we should design improved rats. Maybe we should design rats that they will also pay attention to the noise when they are eating, and then they will pass successfully the Garcia experiment. Maybe we should also ask the rat to be sensitive to the light conditions and temperatures and time of day and so on. And then we'll have a very sophisticated rat that pays attention to everything and can detect all patterns. What will happen to such a rat that pays attention to all of those parameters? Will it be able to detect, to attribute the right cause for feeling sick? It will not, and the reason is that now that you're looking at all those parameters, every food tasting will be an outlier. Every food tasting will be different than anything the rat has encountered before. Because if you have many variables, every time it's a different combination of those variables. So somehow, by focusing on only one or two variables, the rat was able to detect the cause for sickness, while extending the scope of what we monitor would have confused the rat completely. And we are trying to draw conclusions from this to how machine should learn. So the improved rats, of course, will not survive but if they have too many attributes, every tasting of food will be an outlier in some respect, and they will not know which tasting should be blamed for being sick. So this principle that you should focus maybe on simple explanations was already noticed a long time ago by William of Ockham in the 14th century. And he said something in Latin that people tell me that it means entities should not be multiplied unnecessarily. And the way we interpret it today is saying we should always prefer the simpler explanations. If we have to choose between different explanations, I should choose the simpler one. If the rat can explain the sickness just based on taste, on smell, it should not pay attention to other attributes. And we want to turn it into some tool for machine learning. So the question is, why is it the case? Why prefer shorter explanations? Is it a good policy always? What if we have different notions of what's simple? I mean, for some people, an explanation that is an equation will be very simple. For others, an equation will be a very complex explanation. So how can we have such a rule when we haven't defined what we mean by simple? And it turns out that, OK, so I want to emphasize this rule before I go into the discussion of the importance of the language that we use for simplicity. So I want to talk about some trade-off between accuracy and simplicity. So assume I want to find the rule that generates these dots. So one rule that I can come up with is say, this is the rule by which I generate the dots. Another rule could be, this is the rule by which I generate the dot. Another rule could be this one. And we see that the simpler the rules are, the red line is the simplest, the least accurate they are. Because to be accurate, you have to be very complicated and follow all the points. But which one should we use for prediction? I mean, our real goal is to be able to predict whether this new point will be on our curve or not. And which one should we predict for prediction? So good models should be able to do prediction well of new data, and we have a trade-off between the complexity of our model and its ability to accurately describe the data that we have seen. How does this trade-off relate to our ability to prediction? So let's look at another example. So assume I have all those dots which are red or blue, and I'm trying to predict the label of the new dot. So one way to provide a simple explanation would be I will divide it into squares. I will color each square by the majority color of this square. And now I predict that this new dot is going to be blue, because this is the majority of its square. But I could take a more complex explanation and divide it into smaller squares. And again, color them by the majority. And now suddenly I'll predict that the dot is going to be red. And the question is, what the Occam razor is telling us, prefer the simpler explanation. So why should we prefer the simpler explanation? Why is it doing a better prediction? So we're looking at this curve of accuracy versus complexity. We have seen that the more complex we are, the more accurate it can be. So we get such a curve. But what happens with prediction? So if you have only limited data, it turns out that the models that we can represent with the data, the accuracy at some point begins to degrade. What happens is that if I'm trying to predict with models that become more and more complex, at some point I begin to overfit the data. My model begins to follow the randomness of my data, the noise in my data, and its ability to predict goes down. And that's basically the Occam's principle. When I have to choose between a complex model to a simpler model, if they both fit the data similarly well, I should prefer the simpler model. Because as the models grow more complex, the ability to predict goes down. But we will try to make it more precise. So it turns out that even if we have different notions of what's simple, like different representation languages, the Occam razor with respect to any of them is still a good learning strategy. It's quite surprising. So it doesn't matter what I call simple and what I call complex. I should always prefer the simple explanation. This sounds like I'm contradicting myself. Whereas the catch is that we have to define our notion of simplicity before we see the data. Before we see the data, we have to define what's for us is simple or not. And then there is always a risk that in some representations, I mean, we need the representations in which we will both be accurate and simple, and maybe under our presentation we will not find such an explanation. So the nice thing is that no matter what language you pick, if you pick your notion of simplicity before you saw the data, it's a good strategy, it's a good policy to always prefer the simple explanation. And it's not a contradiction or something strange because of this order of things. I have to pick the description before I see the data. But why should I care so much about description lengths? Is this the only thing that matters? Well, it turns out that there are other niceness principles that could work just as well. Not necessarily the shortest of the description, not necessarily the simplicity of the description. There are many other, and we call them regularization principles. So regularization principles are some kind of rules that we follow to prefer one model over other models. And some of them I describe here. So one of them is, for example, if you have some prior knowledge about which explanation is more likely and which is less likely, you will prefer the explanation that following your prior knowledge is more likely to be a good explanation. Another one is notion of a large margin. If I have an explanation, it classifies positive points from negative points, I will prefer explanations that have a large margin that do not go very near to the points positive and negative. Another very common and very useful rule for regularization is to prefer predictors that are sparse. So what do I mean by a sparse predictor? A predictor that uses only few of the attributes of the data. That's what the rat was doing. The rat was using a very sparse predictor. Sparse in the sense that it was only paying attention to few of the variables. So each of them is just as good principle for choosing hypothesis as the shortest of description. And these are called regularization principles. And indeed, we can prove that they work. So what kind of proof we can give? We can give a performance guarantee. For each of those regularization principles, we can prove that it will predict well, provided the two conditions hold. One condition is that the principle was picked before we saw the data. And the other one is that we need to have a predictor that performs well on the training data, doesn't make errors, lots of errors on the training data, and yet looks good from the point of view of the regularization principle. So if I pick the principle saying I'm trying to find a predictor that uses only few of my variables. I have lots of variables, and I have lots of variables. When I see someone, I'm trying to predict whether they're going to be nice or not, and I take some notion of regularization. I would like to have an explanation that is based on as few attributes as possible. But there may be a situation that each of the nice regularized principles does not perform well on the data that I have. So I need to find something that both performs well and looks nice from the point of view of regularization. And so all of them work. The next natural question to ask is, which should work best? Which of them should we use? If I want to design a computer that learns, I know that I have many principles that each of them could direct me towards good predictions. They give me different advice. One of them wants a short description, another one wants large margin, another wants sparse classifier. Which one should I pick? Which one works best? That's very important for us. And it turns out that there is no best. We can prove that there can be no principle that will be best. So things are more complex than we could hope. I mean, we have principles that all work. They can give us contradictory advice. And we cannot tell in advance which of them will work best. So let me first focus on what do I mean by we can show that there can be no best. So this is a basic result that kind of motivates a very important understanding of machine learning, and that's the no free lunch principle. What's the no free lunch principle? It says that no learning algorithm can be guaranteed to succeed on all learnable tasks. So if we look at it at the first glance, you say, no learning algorithm can always succeed. That's no wonder. If I take a learning algorithm and I try to have it predict the outcome of a coin toss. So I toss my coin, feed my results to the program, and want the program to predict the next coin toss. Of course, it will fail. But I'm only restricting attention to learnable tasks. So even if we only focus on things that can be predicted, there is no algorithm that could be well at predicting all of them. In other words, any learning algorithm has a limited scope of phenomena that it can capture. And this is called inductive bias. So every learning algorithm is limited. There are things that can be learned, but this algorithm cannot learn them. In other words, it means that we need some prior knowledge to do learning. Because maybe we are applying an algorithm that for the phenomena that we are trying to learn is exactly where this algorithm is failing. And we can also conclude that there is no best learner. Because for every learner, there will be something that can be learned. Another learner will learn it. But our learner will fail. So the moral from this no free lunch theorem, and it's a theorem, we can prove it, the moral is that it's inevitable to have some extra prior knowledge. We cannot have a universal magic machine that will learn everything that can be learned. And that's a very important moral. For every learning algorithm, if I try to more precisely state it, for every learning algorithm, there is a perfectly predictable labeling function such that when I give it training data which is labeled according to this target function. So I give it correct information. I train my algorithm with data from the function that can be predicted. The expected error of my algorithm when trained on this training data is about 0.5. So for every learning algorithm, there is a phenomena that can't be learned, can be perfectly predictable. It's deterministic. And when I feed this as training data to my algorithm, its performance will be just as good as if I just toss a coin to predict. So the situation is as bad as one could fear from, right? And the problem is that I think that naive expectation for machine learning is not taking this into account. So I was trying for about 2 years to collaborate with people who are doing medical research at Western University in London. Because I feel that I'm doing all this theory and I want to help humanity, and maybe medical research is very important. And it was not going anywhere. And one of the reasons is the state of mind that we have. It's something, they tell you, I'll give you my data and you will crank up your machine and give me some meaningful insight. And I'm trying to say, I cannot work like this. So they tell me, OK, if it doesn't work, I can give you some more data. And they give me some more data. And they try to find what causes Alzheimer, and I don't know anything about Alzheimer except knowing my father. And how do I work? So I tell them, if they give me more data, it still doesn't work. So what's the conclusion? If it doesn't work, we'll try another advisor. They're learning. Right. So my first moral from this talk that I want to pass on to you is that there is necessity for domain-specific prior knowledge. Without it, we cannot guarantee successful learning. So I think the next question we should ask is, how should we model prior knowledge? How should we model it? We want to somehow have a formalism to express it, to take it from the domain expert to the machine learning algorithm developer so that it will be useful. So we need to follow two principles. We need to find some way of describing tools for describing prior knowledge that on one hand, they are intuitive to the domain expert. We want something that makes sense to the domain expert. I cannot tell the doctors that I want some notion of similarity that is positive semi-definite, because the physician, it will not make any sense for him. And on the other hand, we want this notion of prior knowledge to be useful for the learning paradigm. And the quest for such notions, for such tools for transferring prior knowledge is very difficult, very challenging, and this is in the core of what we're doing in machine learning. So next I will describe some tools that we have for capturing prior knowledge, for doing this job, for taking the prior knowledge from domain expert and making an algorithm out of it. The first one and the simplest one was already proposed by Valiant. That's what Valiant got his Turing Award now for in '84, and that's an hypothesis class. So I take a collection of hypotheses and I say I restrict my attention to predictors, to rules that belong to this set. So for example, if I want to predict who is going to be a good basket player or not, I can say I restrict my attention to some rectangle in a space that has only two variables, the height of the player and the weight of the player. And in this space, I will only look at rectangles. Good basketball players will have height between this and that, and will have weight between this and that, and I'll only predict with such rectangles. So I restricted my attention to predictors of a certain type. And if the restriction is strong enough, it contains a lot of prior knowledge. It could be not correct, or it could be just prior belief, but this is one type of restriction. Another one that we already mentioned is regularization principles. So each regularization principle implicitly talks about some prior belief that we have about the data. If we believe that we have a good description language, the belief that we have a short description for the phenomena is actually the same as believing that our language is kind of appropriate to describe this phenomena. Or the regularization principle of having large margins, I will talk about it maybe a little bit later, or the important regularization principle of sparsity, that we believe that our features are such that in order to detect whether the label is plus or minus, it's enough to each time look at only a few features. Okay, so these are all ways of incorporating prior knowledge tools. Let me talk about some more tools. Completely direction and a different direction in machine learning is the more what we call parameterized machine learning. You have some prior probability distribution over the hypothesis, and your prior knowledge is incorporated by giving different models different weights. Which model is more likely? Or another one is you believe in some data generative model. You believe that your data, say, was generated by a mixture of Gaussians. Each Gaussian was generating points of a certain label. And under such an assumption, it incorporates a lot of prior knowledge. If I want to predict, say, whether a figure that I see is a man or a woman, maybe I believe that there is a Gaussian around the height of men and the Gaussian right the height of women. And under this assumption, I can use the height to kind of predict if it's a man or a woman. So this is a generative data assumptions are a different tool for incorporating prior knowledge. I would like to talk about something which is very useful currently in machine learning, and it's the notion of a kernel. So what is a kernel? A kernel is a way to express my prior knowledge by coming up with a notion of similarity. So I want to say when are two objects similar in such a way that this similarity, when two objects are similar, they are more likely to have the same label. So one way of incorporating this prior knowledge is to define a notion of similarity that I believe that will correspond to having the same label. So let me give you an example of such a kernel. So I want to define the Facebook kernel over people. So I want to define a notion of similarity between people based on their Facebook pages. And my kernel, my Facebook kernel is going to be like this. I will say that the similarity, K, between two people, P and Q, is the number of common Facebook friends that they have divided by the number of Facebook friends that P has and the number of Facebook friends that Q have. So I can believe that this is some notion of similarity. And if I can believe that if I'm trying to predict, say, political views, then people who have lots of common friends are likely to have the same political view. Or if I'm trying to predict if someone is, I don't know, a terrorist or not, maybe they all share the same friends, and I can detect it using this kernel. So my choice of kernel incorporates some prior knowledge. I believe that what I'm trying to predict is relevant to the notion of similarity that I defined. Now, what do we do with such a notion of similarity, with such a kernel? So the kernels are the core for a tool which is called support vector machines that you might have heard of. So support vector machines, or SVMs, they use kernels in an essential way. So what we are doing there is that we take the data with the kernel that was given to us by incorporating domain knowledge, and we embed it into some virtual space, such that in this virtual space, so phi is the embedding. So I embed the person P into some vector phi of P. I embed the person Q into some vector phi of Q. And I do it in such a way that the inner product between those two images is the same as the similarity. So I somehow have a way of taking a kernel, taking such a notion of similarity, and translating it into and embedding into some Hilbert space or Euclidean space, such that the similarity that we have before translates into the inner product. Once we do this, we can work in this space and come up with a linear classifier in this space. And this is the tool of support vector machines that turns out to be very potent in machine learning. And it uses the prior knowledge by taking this input of kernels to define our embedding and then our classifiers. The last tool that I want to talk about for expressing prior knowledge is the emergent tool of deep learning. I don't know how much you follow what is happening. And deep learning is now taking all the headlines. It has been featured in the New York Times, in Nature, in Science, in everywhere. And when you talk to people who do it, when I talk to Jeff Hinton or to Jan LeCun or Andrew NG, the usual reaction that you get is that, I mean, it is working, so why bother with philosophizing about it? I mean, we can prove to you that it works, it wins all the competitions, so don't nag us with trying to find explanations why it works. I still have some explanation that I want to give you. I'll give you some description. So the next image is taken from a paper of Andrew NG, is one of the leaders in deep learning, and it explains how they take images. This is the use of deep learning for images for doing face recognition. So the idea is that your algorithm takes lots of images from the internet, and they are not labeled, just choose on those images and trying to come up with a good tool for face recognition. So how does it work? The trick is that at the first level, you look at pixels in each image, and you're trying to find correlations between those pixels. So the first level, each pixel is a variable, and you try to find correlation between those variables. And then you find very simple patterns. You find that such pixels are correlated. When this one and this one and this one are bright, it's likely that this one will also be bright. So we find some correlations in our data. We still don't have any labels, but we find patterns of correlated features. And then we repeat it on a higher level. So we look now at these images as the inputs. So that was just an image with its pixels. Now we fed the machine lots of images, and we figured out that they are repeating patterns. So now we translate each picture to just the collection of the patterns that appear there, and again, feed it to a detector that is trying to detect repeated patterns over the patterns. And then we get more complex patterns, and we do it hierarchically, and we come up with some complex patterns. Now, then at this stage that we have those complex patterns that we seem to see no more correlations between them, we feed it as the features to our learning algorithm. What have we gained by this? What we gain is that the prior knowledge that we have here is the belief that for the relevant task, say for face recognition, once we have those high-level patterns, we can use sparse predictors. In order to know if something is a face or not, all I need is to tell whether you have two eyes and a nose and a mouth or not. So although I'm collecting thousands and thousands of patterns, for every prediction task, will I just want to predict whether it's a face or not a face, I don't need to use those thousands and thousands of patterns. I only need to check 10 simple patterns of an eye, of a nose, of a mouth, and it will give me a good classifier for face detection. So the idea is that once we collected this huge collection of patterns, we can settle for sparse predictors. Sparse predictors, they need to look only at existence, presence or non-presence of very small number of patterns in order to get a good prediction. So that's kind of the prior knowledge that behind the idea of deep learners, where deep learners take the data, finds correlated patterns, repeated hierarchically, and then you have patterns that you believe that can do good prediction with each time only checking very few of them. And we knew already that if you have a sparse predictor that predicts well, then we have guarantees of success. OK, so this is part one of my talk. And the conclusion is that machine learning is a very powerful tool, many existing and potential applications, but prior knowledge is inevitable. For every successful machine learning application, there are no free lunches. So let me move on to another important issue. My plan is to touch upon 3 issues, but it will get shorter and shorter. So the second one, I will talk about it much more briefly. And the second important issue in machine learning is the issue of computational complexity. So far, we just talked about collecting data. So we focus on the statistical, informational aspect of learning. But there's also, in practice, computational complexity is very essential. If I want to train a car driver, I cannot afford, I want to predict whether I should buy a stock or not, I cannot afford to wait 300 years until my machine will decide whether it advises me to buy or not to buy. So computational complexity is a real bottleneck in machine learning, and we really have to address it. In many applications, that's the bottleneck. That's the problem. Now, why is it a problem? It's a problem because for most of the learning paradigms that I talked about before, training the deep networks, or finding a good linear classifier, or minimizing the sum of your empirical error plus your regularizer. All of those types of learning that I talked about, for each of them, we can prove that it's NP hard to solve the problem. So how do we do it in practice? Everything that we try to do, we find those good tools, we can prove that they work, but we can also prove that they are NP hard to implement. So how do you get out of this? It turns out that we are not the first to encounter this problem, that things that you really need to do in practice are NP hard. And look, for example, there are many things which are theoretically hard, but are practically feasible. One of the, I think, most striking examples is propositional satisfiability. We know that the SAT problem is the queen of NP complete problems. But today we have SAT solvers that do work very efficiently. And today it used to be the case that if you want to show that the problem is hard, you reduce SAT to the problem. You say, if I could prove this, if I could solve this, I could solve SAT, therefore I cannot do it. Today it's the other way around. You want to solve it, you show how to translate it into SAT, and then you feed it to a SAT solver and it does it. So there is a gap between what is theoretically hard and what is happening in practice. And one of my goals is to try to understand something about this gap, where it's coming from, how can it be overcome. Another example is linear programming that some of you in the area but probably know. It looks very hard. In practice, it's easy. Dan Spielman came up with the notion of smooth complexity that tried to explain why is it simpler in practice than it is in theory. What we care about are things like learning neural network training, which is those deep networks, or finding the best linear predictors, or doing clustering. So all of those, the last three are tasks in machine learning. They can also, we need them very much. We can show they're NP hard. How do we overcome it? So the basic rationale is for many practical computation tasks and learning tasks, naturally arising inputs are considerably easier than the worst case. When we talk about computational complexity and NP hardness, it means that there are some very, very difficult cases. But maybe you don't encounter them when you're working in practice. And the question is, how can we distinguish between those theoretical constructs that are so difficult and what you encounter in practice that may be much easier? So how can we define the family of inputs on which the computational hardness doesn't get into play? And so I'm really posing questions there, and then I'll show you some partial answers. So are the properties that distinguish naturally occurring inputs from arbitrary inputs? Mathematicians, theoreticians are very good at designing arbitrary inputs, but do they occur naturally? May such inputs that occur naturally be easy to solve? Can we prove it? Can such input kind of be defined for specific tasks? Can we have a generic definition that holds across many tasks? And I have one proposal of this, and I can show that it works for some cases. So many hardness proofs are based on constructing highly sensitive inputs. So what do I mean by highly sensitive inputs? I don't know how many of you had experience with designing NP hardness proofs, but usually you come up with a gadget. And the gadget is something that's very sensitive. You change something small in the input, and the answer flips. And I'm trying to claim that in reality, when you change your input a little bit, the outcome does not often flip to the other side. So is this the true source of hardness, or just an artifact of the proofs that they are using those sensitive gadgets? Do real input have this property that they are insensitive to small perturbations? Of course, I cannot answer the question, do real input have this property? I cannot prove anything about real inputs. But I will define this property, and I'll show you how it helps to overcome the computational complexity. So my basic notion is the notion of robust data. So what is the data is robust? Assume that you are trying to find a linear classifier that will distinguish the blue points from the red points. Such data as pictured here is insensitive to small perturbations, because even if I perturb my points a little bit, the optimal separator will remain the same. So this is the data that is robust to small perturbations. My claim is that in reality, often we encounter such data. I cannot prove this claim, but what I can prove is that if your data satisfies such robustness, then to solve NP-hard problems on your data becomes feasible. So for such inputs, the NP-hardness flies out the window. So here is a more precise definition. We say that an input I is gamma robust for a problem P if whenever I have an input I prime which is close to I have to define what is close. Here I mean close in the sense that every point moved only a little bit. Then the solution of the two instances is the same. The answer for both of them is the same. There will be the same separating half space that will work for both of them. For such inputs, we can show that the basic result here, that for many NP-hard problems in machine learning and also in computational geometry, there exists some polynomial time algorithm that can find the optimal solution in polynomial time for any robust input. So if we restrict our attention to robust inputs, we can overcome computational hardness. And the downside is that still this complexity depends exponentially on the robustness parameter. So it is not really a full answer, but it can give us a direction of where to search for answers to this gap between the pessimistic prediction of computational analysis to what is happening in practice. So the second take-home message from the second part was that there is a gap between the pessimistic conclusions of worst-case analysis and the success of machine learning in practice. And the major research challenges are to understand the characteristics of practical tasks that distinguish them from worst-case inputs and to try to utilize those distinctions in coming up designing algorithms. OK, so now the third part, and it will be even shorter of my talk, is the third theme is the notion of unlabeled data. So far we discussed learning from fully supervised setup. So you want to learn to find a spam detector, and you are given as input emails that are labeled spam or not spam. But as you know very well, we don't always bother to label our input as spam and not spam. And for Google, for example, it's much easier to find tons and tons and tons of emails which are not labeled than to find emails that somebody bothered to label as whether they're spam or not. And the question is, since we have so much unlabeled data, and for some tasks it's very difficult and expensive to label them, can we utilize the unlabeled data to improve our learning? There is a resource that is very available, abundantly available. Can we make any use of it? And there are several approaches that try to address this issue. The first is semi-supervised learning. Semi-supervised learning says that do we have algorithms that are semi-supervised in the sense that they can get as input some few labels but much unlabeled data, and utilize the unlabeled data to predict, to come up with a classifier almost as well as if they got lots of labeled points. Another direction here is domain adaptation. Sometimes what happens is we have lots of data from some domain, but we want to predict on a different domain. Say I want to develop a spam detector so I can train it on my emails and label my emails spam or not, but then I want to sell you my spam detector. And your emails look different than mine. And your notion of spam may be different than my notion of spam. But I don't want to retrain from scratch. So this is called domain adaptation. How can I utilize what has been learned on one domain to apply it to a different domain? It's another example of having data which is not the perfect situation of correct labels coming from a target distribution. Another such direction is active learning. In active learning, the game is slightly different. You get tons of unlabeled data, and then you choose which points to query for label. So you can say, I get tons of emails. They're not labeled spam or not spam, but then I can go to you and ask, would you consider this specific email as spam or not? And of course, I can do it only for few of the points. Can I use such algorithms that will take advantage of the big amounts of data and allow me to query only few of them for the labels? Now, for all of these tasks, we are again in this old familiar situation. For each of those paradigms, we can prove that in the worst case, it's hopeless. So again, we're in this situation. Worst case, there's nothing we can do. We can prove it. I don't know who cares about our proofs, but we can prove that it's. Why do I mean nobody cares about this proof? In practice, all of those paradigms are being used. All the big companies that have to do prediction, they use unlabeled data, they use domain adaptation, they use active learning, although theoreticians can prove to you, I can prove to you, that it is not supposed to work. And again, what makes this gap, this discrepancy? It's some subtle assumptions about the data that we see in practice is not worst case data. Now, the question is, can we formalize it? So, are the properties that distinguish naturally occurring inputs that allow us successful use of poor data? So poor data is my general name for all this type of non-perfect, less than perfect data. Or can there be properties that hold, such properties that may hold for many learning tasks? And we do have at least one such proposition. That was the PhD thesis of Ruth Urner that just finished this fall. And this is called probabilistic Lipschitzness. And this is a precise way of quantifying how likely are points to get the same label as a function of how far they are from each other. So in nice data, close points will tend to get the same label. Far points are less likely to get the same label. We can quantify it, and using this notion, we can prove that for each of those scenarios, semi-supervised learning and domain adaptation, active learning, there are learning algorithms that under the probabilistic Lipschitzness assumptions are guaranteed to work well. So it can overcome the pessimistic worst case results. Okay, so this is the end of my talk. In conclusion, we considered three themes in machine learning. One of the use of prior knowledge for successful prediction. The other one was computational complexity. And the last one was suboptimal training data. And if all of them, we saw that it's critical to know something about our data. Either something which is domain-specific, we need domain-specific prior knowledge, or some general principles that may help us overcome analytic hardness and come up with good algorithms. And let me finish with an advertisement. If you want to know more about machine learning, this is my book that Amazon is saying that it will come up in May 31st, 2014. So you can already pre-order it. OK, thank you very much.
Can you point to a few or three practical results people you or others have often?
Oh, there are lots of them. I mean, if you call some company and they ask you to say English or French, and they have to figure out what you said, they're using software that was based on machine learning to take your voice and turn it into, translate it to what you really meant. We have automated, Google applies endless tools for, say, automated translation. Again, it's based on a lot of components of machine learning. When you have your tablet and you write in your tablet and the tablet figures out what you meant to write, it is based on machine learning. Because I could not write a program that will really take into account all the peculiarities of your handwriting and figure out what you meant to write. But your tablet just trains. It gives you a suggestion, you fix it if it's wrong, and it learns. So it's really, really practical today. I mean, as I was saying in the abstract, this is on the top priority of recruiting and research for Amazon, Google, Facebook, you name it. There's really tons of applications around us that are already there. I mean, my co-author in Jerusalem is involved in developing tools that are now employed in cars to warn the driver when he's falling asleep, or to warn the driver when he's getting too close to another car. So the applications are all over the place now.
This looks like a learning program, which the program itself learns of
Right.
things and has to.
Right.
I think from your introduction you presented, I got the feeling that the machine learning is when you take that learning program and make it generate a program.
No, what I'm saying, you take the data and you generate a program. It's exactly what you mean by learning a program. You take the data and you learn based on the data a program that will take inputs, a situation of a driver, and will tell you he's falling asleep or not. So the program is generated by learning.
Sorry, Dan, another question?
So when you were talking about the no free lunch theorem, you basically said all these great ways of characterizing prior knowledge, none of them works.
No.
Or none of them works, none of them always works.
Right. None of them
You can
always
say it
works.
that way.
Exactly.
So if I have an oracle that can compute Kolmogorov complexity, would that actually be the thing that would be the perfect
No,
one?
no.
Even that wouldn't be.
Even that would fail. Although, I mean, it will fail in a softer way. So I have a more subtle no free lunch theorem that relaxes the requirement of what is successful learner. And then, under those relaxed requirements, you can view Kolmogorov, if you had something that will solve Kolmogorov complexity, you can view it as a universal learner. But I can prove that any such learning will be non-computable. So it's not just coincidence that Kolmogorov complexity is non-computable, but it will be the case with any program that allows universal learning. Okay? Yes? Yeah.
Well, it's a beautiful talk. I liked it very much.
Thank you.
Now, I have two questions on deep learning. So apparently, there's some misconceptions about, I don't know, the deep learning actually learns unknown concepts. What you presented here is sparse prior knowledge that is some human things.
Right.
And you,
Yeah, no, I think that people, there are people in the, deep learning is very successful. And there are people who are getting a little bit high on this success. And there is a difference between listening to people like Andrew Ng that will tell you that they can conquer the world, and listening to Jan LeCun that will tell, and these are all really leaders in this area. And there is no magic here. The point is that you train on unlabeled data, but the unlabeled data have to be such that the patterns that occur there are patterns which are crucial for your prediction. So if you take a deep learner and you try to learn it on images, and they try to predict whether a number is prime or not prime, it will not do anything. So, and the idea, I think that what I described here is the best way of explaining what is happening there.
Another question on deep learning is, apparently we know that the two-level network is equally powerful as deep learning.
Right.
Does
Right.
the deep learning actually speed up the things a little bit?
Right. So yeah, these are very concrete questions about deep learning. And one of the other components that I did not talk about is the computational problem. Training a neural network, even with only one hidden layer, is already NP hard, as you know. And training a deep neural network is even harder. And it's all about how you cut corners. You don't do the full computation. You do all kind of corner cuttings. This is the art of it. And it is based on prior knowledge, and it allows you to succeed. And somehow this art is more easily manipulated on deep nets than on shallow nets. But it has to do with the human factor, as far as I can tell. Right, right. And we don't have a way, I don't have an answer of how can we prove that natural data is such or not. The only way we can go about it is say, here are algorithms that under this assumption should work, and we see that they are working in practice. But I agree. I mean, I'm not a nature scientist. I'm not one that knows how to go to the world and investigate what the situation in the world. I'm doing the theory and right. The only evidence I have is that those algorithms really work on practical data.
David?
Does this robustness parameter, that is known, for example, in SAT to the phase transition and things like that?
The problem is that I cannot apply it to SAT. I don't have such results for SAT problems. It is only applicable to computational geometry problems when you have Euclidean distances and some kind of regularity. It is a very interesting challenge, and I was trying to embark some of my PhD students on this, but they were smart enough to decide that it's too difficult. Yes?
You know, when you talked about probabilistic Lipschitzness, so the question is, data can be Lipschitz, but if your rule does not map that in a continuous sense, you're not going to get Lipschitzness or closeness of solutions of your rule.
Right, so I didn't define exactly what I mean, but I mean, you look at the function of the label as a function of the input. So Lipschitzness will tell you,
in that sense.
Right, in that sense. Yeah.
You talk about needing prior knowledge that allows you learning, but doesn't prior knowledge itself have to be learned?
Right, that's a very good philosophical question. You can ask, how did the rat acquire its prior knowledge that taste and smell are relevant to feeling sick? And probably it's natural selection over ages and ages and ages. And we can come up with this amount of data that is needed for this, but we can't overcome the computational time bound. So maybe by training over thousands and tens of thousands of years by natural selection, nature did computation that we cannot really simulate on our computers in realistic time.
If I understood it correctly, what you said is that every learner is going to essentially make a mistake on some task. There's going to be some task or some input on which is going to make a wrong decision.
Not just input. I'm talking about a task, and you feed it with training data from this task, which is randomly generated, and it's going to have prediction probability of half.
Okay. So does that mean every autonomous car is guaranteed to crash at some point?
It means that every autonomous car, you can create a situation under which it will crash. But that's but it's also true for any human-driven car. But there exists a task, and this may not be a task. That's where the prior knowledge comes in. I'm telling the car that the type of task that you are going to encounter are in a limited scope, and therefore maybe we can handle it.
We have time for one more question.
Yes.
Can you quickly characterize the difference between your book and the computational machine learning book by Collins and Perseverance?
Oh. Right. So the Perseverance book is now 20 years old. And okay. And we try to connect principles to the tools that work today. And the book talks about the principles, but doesn't push it all the way to explain the tools that actually work today, like support vector machines, like deep neural networks, like tools like this. Anyway, that's my short answer.